given information before with a CSTR. All right, so where do we start? Design equation. dx dv equals negative RA FA naught. What's next? What? CA, and then what?
I'm thinking CB just assuming it's
Yeah. Okay, and now stoichiometry allows us to write concentration of A is equal to what?
CB.
Yes.
0.5 CP. 0.5 CP.
0.5 times the total concentration? Yeah, but it's not useful to do things in terms of total concentration for this problem. When do I want to do things in terms of total concentration? Gas phase. Because I can use the ideal gas law to get the total concentration. This isn't gas phase, so it's not very helpful. Yeah?
Is this going to be FA 1 minus X over V naught, right?
Yeah, it's FA naught. Well, to write it more generally, let's just start FA over V dot. A little bit of review. And so FA becomes FA naught times 1 minus X.
Over V naught times 1 plus epsilon X to epsilon.
Are you sure? It's liquid.
But I'm saying that it doesn't matter because it's
It does matter though, because if it were non-zero and you put in the 1 plus epsilon X, you'd be wrong. So you do have to think about that. You're right that in this case you got lucky. But you know, if this were A to 2B, epsilon's not equal to 0, we still don't put the 1 plus epsilon X term. It just doesn't show up for liquids. Neither does the temperature transformation, right? T naught over T or P over P. So yeah, we just have V dot, the initial molar, the initial volumetric flow rate. And of course, this term is what? The initial concentration, 1 minus X. Okay, so let's combine. And we get dx dv. And so now we just write all this together. K times that squared because it's CA times CB, and those are the same. So CA naught squared times 1 minus X squared divided by the initial flow rate of A. This flow rate's not from here, but from the design equation. Just so that doesn't throw you off. All right, so there's our material balance, written now as a function of conversion, but we haven't written it as a function of temperature. Do we need to?
Yes.
Yeah, I mean, it depends on how you're ultimately going to solve the problem. When I do this on Excel, I usually don't do that, right? I mean, you guys saw me last time. I just made a column for the rate constant. So you can do it explicitly, or, you know, what do? We just write out to the side, what is the definition of K?
Wait, why don't you put the T's in that equation?
Well, the T naught over T,
Yeah.
because it's liquid phase. You only have to do that if it's gas phase.
Why?
Because for a liquid phase reaction, the temperature doesn't significantly change the concentration. It does, but it's subtle, right? Same as changing pressure, doesn't really change the concentration. So we've neglected that all semester. We're going to continue to neglect that. But for a gas phase system, temperature and pressure have very big impacts on concentration. So we have to explicitly account for that.
True.
It's also why the epsilon X term is negligible. We're making a few more moles, who cares? It is true that molar densities might be different for our reactants and products, and we might actually see some differences in the volumetric flow rate, but again, those are usually negligible. Okay, so this is A times the exponent negative EA over RT. Do we know everything in that formula? We don't know A, right? So how do we get A? We're given a K at a specific temperature, so we just put K divided by the exponent negative EA over RT, and we're given the activation energy. If you do all of that, the number you get for A is 1.93 times 10 to the 5th, and it has the same units as K, liters per mole second. So yeah, from what we're given, we can calculate A, and now we know everything in that equation. Of course, temperature is still there, but that's okay. And which R do we use, just as a quick review? Yeah, but what is EA? So we want to use R based on calories. I don't think I gave you guys R last time, like in a table. I'll make sure to do that on the next exam. The back of Felder and Rousseau is where I always go for that. It has R in like 20 different sets of units. The number, if you like memorizing things like I do, I actually hate it. I've just used it too many times. In cal, it's 1.987. In joules, it's 8.103. Or 301. One of those. 301. 314. You guys can tell how much I care about precision in my research. 8 is fine. Just put 8.
What was the score in Clemson between FSU?
Oh,
I bet you know.
that's a good question. I was there, but I don't remember the score. I know we won by 3.
Forgot?
34 to 31. What was it?
37, 34.
I know we won by 3. Are you kidding me? That game took years off my life. I don't want to remember the score.
How did we get to this score?
Why? Were you like, no, and they're like, yeah.
Yes, that's exactly right.
Wait, so what?
I'm standing there in orange in the middle of 80,000 FSU fans, and they all hate me because anytime anything good happens, I'm screaming my head off, and they're just like,
Good. Wait, how did we just get to that?
how do we get to what?
To the FSU discussion.
I don't know. He asked me.
Oh, because you said you were good at memorizing, but then you couldn't remember whatever that was, so then I'm like, I'm just gonna ask.
I went to Clemson. He might remember that, so I was just at the game. Anyways, that is R that we want to use for this problem. So we've got, where do we want to go next? We've done our material balance. What's next?
Energy balance?
Okay, so one of the ones that let's first, before you write out the energy balance, it's good to calculate delta CP. Why? Because it's often 0 and it significantly simplifies your energy balance equation. So let's do that. What is delta CP equal to? The sum of the stoichiometric coefficients times the initial or the individual heat capacities. And what is that equal to in this case? 30 minus 15 minus 15. Okay, so now let's write out the energy balance. So for the special case of delta CP equals 0, adiabatic reactor, all the initial inlet temperatures are the same. Anything else? Yeah. Shaft work is 0, no accumulation. Okay, with all of that in mind, you get that the temperature is equal to the inlet temperature plus conversion times negative delta H reaction divided by the sum of the stoichiometric coefficients times the specific heats of the individual species. So just to write it out a little bit more specifically, in this case, this sum term is CPA plus CPB, right? Both thetas are equal to 1 for those two materials. The theta for C is 0, so that heat capacity doesn't show up. Do we know everything in that formula? We haven't yet calculated the delta H of reaction. That's correct. So So let's do that real quick. Same exact formula, right? It's the sum of, sorry, not thetas, the stoichiometric coefficients times the molar enthalpies. You can often use here the formation enthalpies if you're not given. This problem just kind of gave you some enthalpies, all at standard condition. And so what do we get? We get negative 41 minus negative 20 minus negative 15. So what's that? Are we sure?
Yeah.
Yeah. I don't know why. I thought it was 25 and 15. Anyways, yeah. Negative 6. I'm like, it seems odd that it would make it so it's exactly one left over, but it's not. All right, negative 6 kcals per mole. If you're setting things up in a spreadsheet, I would almost never put in anything in terms of kcals or kilojoules. You're just going to forget to multiply by 1,000, and the gas constant you use is almost never going to involve kcals or kilojoules. You're going to use 1.987 calories, not kcals, or 8.3 kilojoules, or joules, not kilojoules. So anyway, 6,000 calories per mole. Is there anything else that we need to know?
X.
Yeah, that's kind of the point, right? To figure out, well, no, actually, we're given X. So this specific question is just asking for the volume given in X. Yeah.
We never had the initial concentration. I think they need to give us the flow rate.